It's a huge pleasure to be here. First of all, I should say that I couldn't talk at all yesterday, so I'm really happy to be able to talk at all. I have a bit of a cold, and I'm not going to talk too loud, and I'm told the mic is helping me out here, so if you can't hear, just say something. I think the last time I was at York was, when was that meeting that you hosted? It was like 10 years ago at least.
More than 10 years.
And it was in the summertime, and so I came here, and it's like, is this the same place? I think you have a lot more buildings than you did then. So this is going to be a fairly wide-ranging talk, and hopefully it will all make sense and come together at the end, although I was warned that some of you unfortunately have to leave early. So I'll try and make sense of it. So I've been at UBC since 2000. It's an easy year to remember. And they call me a human-computer interaction person at UBC. And I have a really funny story about that, which is when I was asked to interview at UBC, first of all, I've been working in Silicon Valley at a think tank. And my background was hardcore robotics engineer, so I was a robot engineer. And I had gotten very turned off on academia. I had no intention of ever going into academia again for reasons of my difficult PhD. And so I've been there for 4 years, and then the company kind of blew up, and it wasn't going to work out to stay anywhere. And I had a boyfriend who was at UBC, and he visited me in Palo Alto, and I was walking down the street in Palo Alto, and they said, "Oh, look, you know, I ran into a friend from UBC, and also my husband was there, or my boyfriend, and so we all met on University Ave, and the friend from UBC said, Karon, it's like, you have a boyfriend at UBC, we're hiring." And so they talked me into going and interviewing at UBC in computer science. And I said, this is ridiculous. I've never taken a computer science course before. This is a joke. You're interviewing just to get, show you've interviewed women, right? That's what this is about. I was like, okay, as long as we're all clear on this, that I'm not a fit for this job, and I'm just telling you, I'm accepting this interview so that I can go visit my boyfriend, okay? I'm disclosing. And so I went up there, and it was fantastic, and it was really fun. But and I changed my idea about what an academic job could actually be, and ended up accepting the offer. But the point of the story was that they asked me that we really want you to come and start our human-computer interaction unit. And I said, what's HCI? Because I didn't use that word for it. Okay, we called it other stuff, because I came from a mechanical engineering tradition. And we do design for people. We, especially at Stanford, MIT at that time, were quite forward thinking about engineering for human systems that humans are going to use. You actually have to pay attention to the problems that people have. And we're working in rehabilitation engineering and things like that, where you actually say, you know, why are people not using the artificial arm? That there's actually maybe a reason for that. And maybe you have to go talk to the people and figure out why this wonderful device I made for you, you're actually leaving it in your closet. And so that was really baked into me from the start. But I found that in computer science, they do the same basic ideas, but they call it something different. And so my job then became to translate. And so, so call me an HCI person. My actual history, like John said, is I've been a lot of places and done a lot of things. And then it's all kind of a big mosh pot. And now I say that I am a robotics engineer doing psychology in a computer science department. And that's kind of what I do. So my lab is called SPIN, and that's partly because I was, when I first started Haptics, my work with Haptics, which is force feedback interfaces, I worked in a robotics lab at MIT, and at MIT at the time, I think it's still true, your self-worth is equated to the number of degrees of freedom in your robot. And I was really interested in knobs. I thought, if you have a very simple device that's cheap, and you could put it anywhere, and it won't break easily, then how powerful would that be? But then you have all the hard work is behind the scenes. It's in how it works, because you can't see it. It's not obvious it's not literal. You actually have to build up a conceptual model in someone's brain about what it's actually doing. And that's really interesting, and it's hard. But the people at MIT said, it's a knob. How can it be hard? So I defiantly called my lab the SPIN lab because of knobs. And so sensory perception and interaction, which is pretty broad. So we do a lot of stuff. In particular, I'm going to, kind of something I've come to in the last 5 years, or more than that, more like 10 years, is the importance of affective computing and touch in the affective sense, and really trying to get more understanding of what that is and how it works. So I live in a lot of worlds: human-computer interaction, robotic design and controls, and mechanical and interaction design, and you're going to see threads of all of that. But design is probably the big thread pulling it together. And what is haptics? It's our sense of touch. I think probably most of the people in this room will have at least heard the word. I remember when I did my first job interview when I was finishing my PhD, there's this little guy in the back who says, "What's haptic? Is that a liver disease?" And I had to explain that I didn't know anything about liver disease at all. And so, of course, haptics is very important in the natural world, in our interactions in the natural world. But most of the time when people hear haptics, of course, what you're thinking about is this thing buzzing, right? That's kind of the experience that most people have haptic interface. And maybe if you work closer to the field, you have seen some force feedback devices that sit on a desktop, and you can actually feel a graphical interface with them in some way. Who has actually seen something like a Phantom Omni or no? Yeah, so you know what I'm talking about. But that's what most people feel. You know, we're far way away from what we can actually do in the real world. And so I've always been very motivated to say, well, first of all, how can we come closer to the real world? But also, if you get tired of always using a keyboard and a mouse and just kind of touching this very indirect way of interacting with digital technology or just about anything you're trying to do, and especially as things are getting more and more embedded in IoT, wouldn't it be nice if you could have more direct interactions? Would you have more control? Would it be more intuitive? And what would that mean? What would that be like? So I'm working in human-computer and human-robot interaction and doing design, ways to communicate through touch. So communication has always been a big thing. And part of it has been studying how people communicate through touch, both social and functional and emotional. And then actually how you can do that with technological support. And then the other thing that's really been a pivot over the last 2 or 3 years, I would say, maybe a little longer than that, is realizing that over time, we've built a lot of tools in our lab to design content for different kinds of interfaces. I think we probably do more of that than anyone else. And realizing that now there's a real need for understanding how to design haptic stuff, not just designing it, but how to design it. And so the second part of my talk, I'm going to get more into that. Okay, so start with a story. So I think it was about 10, 12 years ago, I get a call from a guy who's in Texas, and he wants to be a grad student. He wants to come work in my lab. And it was a pretty interesting conversation. He says, you know, I found your webpage, and it looks like you're kind of doing this thing on affective touch, or a little bit of that. And I just had this idea, you know, I had a girlfriend, and she had a cat, and I really liked the cat. It was really cool. The cat was really cool. And then my girlfriend left me, and she took the cat. And I've been thinking a lot about this cat. And when you pet the cat, it does something to you. I just want to understand that. And so I thought, well, this is just such a crackpot thing. You always have to have one of those in your lab, right? So he came and really transformed what we did. You know, we're on the quest for understanding what's the deal with a cat. And so think about it, that it wasn't quite as off the wall as that. By the way, since then, the whole thing of affective computing and social touch has become much more mainstream, but it was not mainstream. And affective computing at that time was quite an unusual thing and not getting a lot of respect, I would say, in the research world. Not that that's ever stopped me. But at the same time, I was starting to be aware of all these studies that were coming out about if you have cancer and you are studying people who have cancer and say what's affecting the survival rate, what are correlates with people who are cancer survivors? You know, is it the kind of cancer you have? Is it the treatment you got? Is it how severe it was? What are the factors that influence if you're going to recover from cancer? And they were seeing, well, one of the factors that is surprisingly important is, do you have a dog? Okay, and same thing with heart disease, okay? I think the study I saw there was about cats. Having a cat made a big difference. It was a surprisingly large factor, just a co-correlate. Like, we don't know what the causality, we don't know why. Nurses know that touching is important. We know that in early childhood development, if a baby is deprived of touch, very bad things happen. There's some terrible studies that I'm sure people are aware of rhesus monkeys from the 60s, where they looked at this, and there's a tremendous need for physical contact when you're young, vulnerable, developing ill. But why? Is it, for example, with those studies about heart disease, is it that you're walking your dog and you're getting exercise? It's that you're feeling responsible for caring for something? Is there something about the actual physical contact that is somehow contributing to that? And how would you even go about studying that? How would you understand what's going on with social touch or physical comforting touch? There's a healing thing to it, but could we understand that? So when Steve came, the guy with the cat, we actually started out thinking we would study real animals and people with real animals, and quickly became disabused that this is not an easy path, because real animals are very hard to study. They're hard to control. They don't always do what you tell them to. And they're also hard to get inside their head and understand what they're feeling and how they're reacting. So we did take a different approach, which I will spend some time telling you about. But I also wanted to come back to Poppy. Poppy sadly, she passed away last year. Poppy's been an inspiration for me. She's a care dog who works at or did work at the Canuck Place Children's Hospice. Sorry, this is a place where children with terminal diagnoses go with their families, or can spend time with their families, and been spending a lot of time there recently. And we were actually invited to come in there because the medical director, was aware of our work with affective robots and thought that there might be a place for them. And it was because of Poppy. It was because this amazing, very unusual dog. And I have followed Poppy around Canuck Place. I've tailed her, shadowed her. You tail a dog. That sounds like a funny thing to do. And been it's almost magical. She has a sense of where to go. She finds the room where she needs to go in and climb onto someone's bed and cuddle with them until she can't take it anymore and she has to go and take a break. She finds the tension. She finds the places where she can help, and she knows what to do. And how does she know, and what is it that she's doing? Like, I'm completely intrigued by that. And so we're never going to build Poppy, but I wanted to try and learn from Poppy and understand some of what she's doing and see if we could do that. So it's always nice to think about, so we'll come back to that later. I just wanted to kind of set that up as an ultimate grand challenge. So affective touch and what you could actually do with it, what it means to people, that's one of my grand challenges. I don't know how many people share that with me, but I think it's a pretty big deal. I actually think it's one of the most important things that haptics as a technology can actually do for us, and learning how to control that, how to leverage it is going to be where haptics has its greatest power. Another thing is learning with haptics. I'll talk, because I have a lot to talk about. I'm not going to go very much into this. This is a really exciting project that we've just gotten going on, so I don't have tons of results on it yet. But, and then accessible design tools, this whole thing of helping people design with them, and I'll come back to that at the end. But I'm going to start with affective touch, which is actually one of the places where we've built a ton of tools. So, so there's Steve. Does this actually work? Yeah, there's Steve. He finished 5 or 6 years ago, so you can see sometimes if you're a PhD student, you can have a very long-lasting legacy on a group of people. So affective touch and human-animal interaction, we actually are inspired by human-animal interaction, but we've used robots to study that and to simulate that because it's more accessible than real animals. And also, rather than we say, well, why don't you study human-human interaction? And there's lots of complications with humans touching humans, and we also have some of the same issues of control and being able to get inside people's heads. And so with the robots, for example, we can actually sense how people are touching the robot and do things with that. So we have been developing this robot modeled on human-animal interaction because people might touch animals in a different way than they touch people, and for different reasons. And so here's a story. I'm trying to kind of tell the basic idea of what we're trying to do in our human-robot interaction. So let's say you have a child. I'll call her Chloe. And Chloe is looking at a little robot. Okay, there's a little thing that can move and it can do something. Okay, and say she's going to. We wonder if we can actually sense Chloe's emotion through the way she touches something. So this is where the affective computing comes in. In order to actually adapt an interaction to a person's emotion, we need to sense their emotion. And there's ways that people are sensing people's emotion. It could be through facial recognition. It could be through putting EEG or other kinds of sensors on your body. It could be listening to voice prosody. Each of these techniques is invasive in a different way. They're all invasive. They're just invasive in different ways. If you use EEG, you've got to like put these things on, and by the way, they're also all very imprecise. Okay, and if it's voice, people need to be talking. If it's other kinds of sensors, you've got to put all this stuff on. Now, if a kid who's having a tantrum and blowing up, all of this sensor stuff is not going to work out. Voice is, has to be controlled. If you're doing facial recognition, their face has to be in front of a camera. So maybe you need to be doing all of these things. But we were really striving for a situation where a kid doesn't have to wear anything. You don't have to make them talk. Maybe we'll add voice into there as a triangulation. And we do need them to touch the object. So we need to make an object that they will touch, and that they want to touch and will touch in an interesting way, a revealing way. So that's the particular thing that we've been trying to understand. So in order to sense emotion, we need to develop cutting-edge sensing and machine learning to actually understand what's going on with their touch. And as we're doing that, we're actually doing a lot of these other modalities at the same time so we can triangulate and understand and get ground truth on what is it that we're actually getting out of the touch. For example, we might put the EEG on not to adapt the interaction, but to check and see how to interpret the signals we're getting out of the touch sensors. Okay, and then you have the bit. We call them kettle bits. It was actually the New York Times that came up, the New York Times Magazine that came up with that name. I say, what emotion, the bit, you could say the bit has, imagine the bit has an AI in it, and the bit is saying, what emotion is Chloe feeling? How would I tell? So we can actually sense what the touches are, but then you have to say, what do those touches mean? And I have to interpret them somehow. I have to relate them to some kind of an emotion model. And that figuring out what that structure, what that framework is, and how we would interpret it is a huge part of the research we're doing at this point. So, and then the bit has to decide, how am I going to react to this? What am I a sleepy, boring cuddle bit? Am I a playful cuddle bit? Am I a cuddle bit with an agenda? I'm trying to help this kid do something. Maybe I'm trying to get them to calm down. Maybe I'm trying to get them to wake up. Maybe I'm trying to do something else. But anyway, somehow the bit gets to be itself and decide how it's going to react. Once it's understood Chloe's emotion, it has to respond to it. And then it has to render how it's going to respond. It's like maybe the bit decided that Chloe has hit it, and so I like slapped it, and so I'm going to cower and I'm going to be terrified. So the bit needs to be able to render terrified somehow physically through its body, okay, in a convincing way that Chloe can recognize. And so it wiggles, and then Chloe actually has to perceive this through the way she touches it. So she touches it, she goes, oh, I've scared it. Okay, and she can actually tell that. And then that goes back into her brain, and she interprets that and decides what she's going to do now. Is she going to try and stop scaring it, or is she going to try and scare it more because that's fun, and she's mad, and she wants to hurt it? So and then you have this interactive loop, and we're trying to understand how that loop could go. And so in making our little bits, we're trying to make very simple, small robots that anyone could make and customize and make their own, and actually understand how that relates to their attachment to it. And a huge part of the research there is how do you actually create expressive motions, movements that you feel, and how do you customize them, and how do you build the robots so they can render those things. The bot has to have the ability to display the emotions that are relevant. And then you have to create them motion, and this is actually not easy to do. As an engineer, I know that, if I'm trying to make a pick and place robot that kind of picks something up and goes over there and sets it down again, you can do that through all kinds of specifications, use a vision system or sensors and kind of figure it out. But if you're trying to do something very subjective, like showing that it's terrified, that's kind of in the eye of the beholder. Maybe different people would perceive it different ways. How do you come up with the specifications for that? What's the design space? So this expressive motion planning it's not unique to haptics, of course, but we've been trying to do it in the context of things that we would touch. And of course, we borrow a lot from animators and artists and people and actors, actually. In fact, we'll show you a project where we're using voice actors to help us figure this out. So you have this virtuous loop that we're trying to understand. So here's another simple picture of it. This is basically the same thing I just showed you. So you have the person is expressing, recognizing, the bot is recognizing something, and then the bot has to decide what to do, expresses it, and the person has to recognize it, and it goes back around. And so the robot platform allows us to study these individual elements. We can break it up and look at the different parts of it and then put them back together in some kind of synergy. So the first time, well, this is actually more like the third or fourth version. This was one of Steve's robots. We call it the Haptic creature, and I call it a turtle with a fur coat. It was using the technology of the time, which you can see it's fiberglass shell with a bunch of FSRs. Who knows what an FSR is? It's called a force-sensitive resistor. It measures force, so the pressure you put on it. There's these like little Band-Aids that you stick all over. It has to be a rigid surface. You press on that sensor, and it sends out an analog voltage, which is related to how hard it was pressed. Now you can see some problems with this. If you're just trying to be a touch sensor, look, there's all these blank spots where there's no sensor. Of course, if you tap the shell, it'll vibrate it, and of course we have an accelerometer in there to pick a few accelerometers to pick up the vibration. But as a touch sensor, it does leave something to be desired. It's also, it has to be on a hard surface, so what you touch is solid. It doesn't feel like a real physical mammal. And we tried putting, a neoprene cover over it so that it would feel a little more flesh-like, but it turns out the sensors don't work so well then. And so, surprisingly, we got surprisingly good results out of this, but you look at it and say, this is really not what we were looking for. And so we've done a lot better since then, but this was the first version. And then the rendering, on the rendering side, we did many, many prototypes and mock-ups to try and figure out what the emotions should be, the movement should be to display it. This is a computer science student who had never built anything in his life before, and he eventually became proficient enough to be able to build this machine. And so we've tried very careful not to make it look like a real, no particular real animal. It's kind of androgynous, non-specific sort of ethic to it. But it looks like a mammal, so you have certain expectations about how it might move. And so it's what you might think of as kind of its butt moves like in a breathing wave, which is kind of a little bit weird, but we were trying to shake things up and have people not make too many assumptions when they came to it. And it would, its ears would kind of perk up or get solid or go slack to signify a kind of a level of arousal and attention. And it has a heartbeat, and it people always ask if it could get hot or cold, and I will tell you that when you wrap this many motors with that, you do not add heat to it. Instead, when you're doing a demo session, you have an ice pack ready to set it on every once in a while, and you have two of them running so you can have one cooling off while the other one is going. So it was warm. But so this was, we got a lot of great research out of this one. We call it version 1.0, even though there was lots of versions before it. And then we set out to answer 3 questions. How do people interpret the creature's emotion rendering, and can that be consistent? How do people display particular emotions to the creature, and can we actually move their emotions? And there's 3 seminal papers that came out of this, and I'm going to kind of do some highlights, touch on some highlights of those. So, so who is familiar with affect, like 2-dimensional models of affect? Has anyone encountered that? There's a little bit of familiarity in the room. So I'll just cut to the chase right now and say we're throwing these out now. Like one of our developments is that we don't think this has a lot of value anymore, but it's what the field has been using for a very long time. It's kind of what's quite accepted in the psychology, emotion psychology field, and we stuck with it for quite a while. And it's actually helpful in terms of just sort of thinking about emotion. So you have arousal and a valence. Arousal is basically how much, and valence is which direction, and you can put most emotions, you could kind of set them down somewhere in this 2-dimensional space. There's a 3rd dimension that is often used, which is dominance. And dominance would be like the difference between distressed and enraged. Okay, kind of how much power is being expressed by it. And is that a question? No, okay. So by the way, if you have questions, please do jump in. And so one of the things that you have to think about when you're trying to render emotion, whatever the medium is, whether it's a smiley face on a screen or a robot that's moving around, is do you have the capability or the movement ability to actually do this? And we really were not able to express high dominance emotions with our robot. It couldn't show hostility, for example. It couldn't bare its teeth. It couldn't snarl. It didn't have hackles. Although we've done some other projects where we've tried to do that. And given that we were kind of working with kids, it was unclear whether we wanted to make it that scary. So Steve came up with a touch dictionary. I don't expect you to read this, but what you can see is that there's lots and lots of words here, and this is a fairly comprehensive categorization of all the different ways that people could be made or induced to touch the robot. Using video studies, we collected data on our deficient touch sensor system, and we carefully described them. And then we have this dictionary of how people will touch a physical robot. And then we measured the frequency with which they were going to actually do that in order to render particular motions. And what we actually found, I guess I left that slide out here. What we actually found was that we had hoped maybe it would be easy. You know, you can always hope. Maybe we could figure there would be a correlation with what emotion people were trying to represent and the gestures they used to do it. And we have things like cradle, finger, grab, hit, hold, hug, kiss, lift, massage. Kiss happened a lot, by the way. Pat, pick, pinch, poke. You know, all these different things that people could do. Is there going to be some sort of, you know, connection between the emotion they're trying to display? And the answer is, for the most part, not. I think the one thing is that if people were distressed, they would always pick it up and kind of hug it, even though it was quite big. But even that, we figured, you know, if you have a different sized robot, maybe they would do a different thing with it. And so there wasn't a lot of, we couldn't just measure what gesture you're making and be able to infer the emotion. Since then, going on after Steve left, we have gone through a couple of versions of this. One is that we found that there was far more information in looking at how people made the gestures than which gestures they made. Like if they made them harder or faster, then that would be different. There's very high individual differences, so you really need to train up a personal model. And now we're actually looking at changes in models over time. So you're actually looking at how people move their expressions rather than any absolute thing. So you're looking, are you becoming more distressed rather than are you distressed? And recognizing also that people are feeling a multiplicity of emotions at one time and that it's a dynamic thing that kind of rises and peaks and falls down rather than just this static snapshot of things. In the real world, it's very different. And that's why these static two-dimensional models are not working for us in practice. But anyway, so during this time, people would actually come through the lab and say, wow, this is really cool. We could use this. Like, have you thought of using this for kids with autism or people with chronic pain? There's all these things that could be helpful. And up to this point, we've just been looking at kind of, you know, trying to understand emotional touch generally. And now that people are saying, oh, there's therapeutic possibilities, we thought, well, sure, that would be really cool. Like, who could work with us on that? And so we started working with a group. The first group I tried to work with was at BC Children's Hospital. It was actually anesthesiologists. And so anesthesiologists have this problem where pediatric anesthesiologists, where they have kids coming in for surgery, maybe not their first time, probably a serious surgery, and a kid is terrified, the family is terrified, and a kid doesn't want to undergo the needle or the mask, and they're fighting it. And there's terrible bad things happen if the kid is fighting the anesthesia. They resist, and then it just kind of screws everything up all the way down. The recovery, the surgery doesn't go as well, the recovery is slower, and there's just more difficulty and more stress. It's very important to reduce stress at this point. And so what people do is distraction, there's pharmaceuticals, but you really don't want to be giving more medication to these kids. And so they were very interested in the idea of could something like a robot actually help a kid calm down. We had this whole plan about how they could have the robot as they're going in, and they could hold on to the robot as they're going into the room, and they could have it with them when they're coming out again, and they could have it through their whole recovery, and this would be really interesting. We could collect all this data. And I still want to do that, but it was actually very difficult to get funded for this because this is one of these things, a little cynical hat for a second. Don't you dare do research that crosses over between engineering and medical research. And good luck with getting that funded. So we haven't done that particular study, although we got pretty far along it. But in the meantime, we realized that we needed, if we were going to do that, we needed a robot that was much more capable in particular ways than our first haptic creature. We needed one that could actually do interaction design. In other words, we have to craft out a story. So when we did studies with kids with a haptic creature, kids would always ask questions about it. They needed an origin story. What is it? What kind of animal is it? I don't know. You tell me. What do you think it is? Okay. They'll come up with something. It doesn't matter. It's important that they have it. And they say, why does it have it? The haptic creature was tethered, so it had a power and data plug. It was disguised as a tail that revealingly plugged into the wall. And so they would say, And like you turn in between sessions, maybe you have it turned off and it's not kind of doing that little hum of the motors, and they say, is it dead? You turned it off. Is it dead? And it would be very distressing to a young child. Like, but then they needed a story. There needed to be a narrative. And it sounds like as a parent, I had young kids at the time, and it was kind of a duh moment. Like, why did it take me so long to figure this out? That if here we were treating the kids like adults, really, just thinking we'll come in and we'll do a trial with you, but we're showing something that they're putting agency into. They're treating it as a real thing, and they really needed this story around it. And so I think that we understood this much better going into our second design and say, if we're going to put this in a hospital with kids, they need a reason to come up and pick it up. There needs to be a story. There's a narrative. It needs to be acting. This is an actor. It's a robot that needs to act. And so basically, we had done a study that showed that the breathing was very important. If you put this robot in its breathing in a particular way and the kid holds it, that their stress goes down. It calms them down. So we did show this calming thing. Like, it's like a pill, okay? And so we needed to get the kid to take the pill. That is, pick the robot up and hug it. So how do you get a kid who doesn't want to come and on their own voluntarily pick up the robot and hug it? So we had to make that story, make that narrative. So we thought, okay, with a robot, it needs to look appealing. Maybe it needs to look really scared, and maybe it needs to have an orienting response so it can actually look over you. It doesn't have eyes, but it can still orient. And then once you pick it up, can it cuddle like a robot, like a cat? Will it kind of rub its head against you? So there's all these different things that we needed it to be able to do, plus it needed to be able to render these different emotions. And one thing that we really wanted to try was to kind of show the difference between being frightened and kind of like very, very closed in and very closed body posture, and then just like kind of, I'm fine, I'm relaxed, I'm open. It's kind of a cat-cow yoga thing. And so we wanted to give it a spine so that it could really kind of have that closed and open sort of attitude. I thought with those highly precise specifications, we thought enough of this having computer science students build sophisticated robots, we'll go to a professional design firm. And I knew that this was a difficult job because I have designed robots and I know what you need in terms of specifications. But we picked very carefully, and there was a team that seemed up for it, and we would do that. It was a disaster. It was a very expensive disaster. We did build this robot. We never used it. The design team had this approach where they wanted to give us one kick at the can. Their budget was such that that was all what I thought was an immense grant would pay for. And so what we needed to do was a lot of sketching, a lot of iteration to try and figure out a system that would allow us to do these different things. And they came up with something and built it at great price, and it was wrong. And so that didn't work out too well for us. We have this, and really what that did was we learned a lot from that expensive mistake. And this was, let's go and concentrate on one degree of freedom and one kind of emotion, movement. The breathing was so important. So we went back and really studied the breathing and came up with this design system that would actually allow us to iterate very rapidly and make all kinds of versions of things and really explore the design space of breathing just one at a time and have these be quick, dirty, cheap. You could throw it at the wall, you could kick it, you could step on it, you could vomit on it, and it won't break. Okay, because this is the kind of use case that we were going into. And so there's a couple of design systems here, and so, oops, I went the wrong way. I'm going to show you a video. There's a sound actually. I don't think this one has sound. And so this idea of sketching, physical sketching. So this is Paul Bucci, who's a master's student at the time. He's a PhD student in my lab now. And so this is just showing some of the way we work in my lab. Is we figured we really wanted to figure out breathing motion. So what do? Do we build one big expensive one? It's not just we wanted to figure out breathing motion. We wanted to make a system that we could then modify a lot and try out different things. So we needed to make a fabrication system that was easy to modify. So I came up with this basic idea that rather than having like a motor has to push on you, instead we have a flexible structure that we can pull on it. And so most of the force is happening in the restoring force of the springs. You're basically pushing on a spring. The person is pushing on a spring, which doesn't heat up or make a motor burn out. And that's why you can step on it, because you're not braking on it. There's just a string in there that's pulling on the spring internally. So you can make it breathe up and down by doing something indirect, okay? And so he's playing with that basic idea. So you have, there's a string that's a little cheap, a tiny little weak motor that's just pulling a flexure up and down. And then you wrap that in fur. And that's basically the idea. But to make that be robust and easily modifiable, and you could make lots of different shapes with it, took actually quite a bit of ingenuity. And so in the results, you have these, I just can't say how much power there is in the breathing motion. There's so much you can do with it. It's just 1 degree of freedom, but you can make it slow and fast. You can change, you can make it be gaspy and irregular and sharp and startled. You can do all these things with breathing. But first you have to have a kind of a machine that shows it. So these are some of the design systems, so you can actually, you know, he did it in Illustrator, but you can just edit it and then throw it out to the laser cutter and build another one. And he had like a round trip thing of like 1 hour to make a new cuddle bit at one point. He came up with 2 ones finally. This one is made out of wood and the other one is made out of plastic that you just cut up. So how expressive are they? You know, this plot takes a little bit of time to explain, so I'm not going to try to, but you can just say that these are different emotions that we try to express. And calm, relaxed, serene, at ease, or sluggish, droopy. And basically, this is 2-dimensional, and you can see where the dots are and where they landed on there. So sluggish ought to be low, kind of neutral valence and low arousal. So you can see where you want it to be. And so we can just see how well did we do with these. And what we found was that we did low arousal was okay, negative valence sucked at. Like, it really didn't do negative valence very well. With these, we could do low arousal, positive valence really well, and high arousal. You can see a pattern here is that we could do arousal really well with this system, but we couldn't do valence. So which direction? Was it excited happy or excited sad? It was really hard to distinguish. And this is a very common result with affective displays. It's often quite hard to distinguish. Yes? Yeah, sorry, I was trying to rush through this because I know that I'm taking too long. The dots are individual experimental results. So what we did here was we showed the robot. So we designed the emotion, and that was a whole, or the behavior, and that's a whole other study, was designing the behavior. And we showed the behaviors that we had designed to individuals who had not designed them, so new individuals, and had them rate where on the affect grid they found that movement to be. And so we were trying to do sluggish. We just showed it to them and said, mark it on the affect grid and place it. And so we knew where we wanted it to land, and we saw what they perceived.
So the different dots represent
different subjects.
Different subjects, but for a common underlying behavior.
Yes. So different subjects seeing the same behavior.
Yeah.
Thanks. I probably shouldn't have shown this slide if I wasn't going to go over it. So basically, valence is harder to render than arousal. A common result. The cuddle bits don't have fangs, and so if we want to do negative, we probably have to design a different system. So that's just, you know, not a super surprising result, actually. So that was a Kai paper a couple years ago. But let's get on to how did we actually design those behaviors? I'm kind of getting ahead of myself. And so another student, Oliver Schneider at this time, had this idea. This wasn't even his project. He just thought it was kind of an interesting idea. It's like how we were trying all these ways, you know, like people sketching. It's a 1 degree of freedom device. Maybe you draw a line, and that's the trajectory of the movement, or maybe you breathe, or, you know, how do you convey what you want it to do? And especially maybe you're not an engineer or a programmer. We just want anyone to be able to do it. And so Oliver had this idea that maybe you take a sound file, like if you want it to behave like a cat, what if you like record the cat purring, and then you have it do another time, and you could actually play that back, and maybe you could even kind of combine or mix like a sound mixer between 2 things that you've recorded. So that was one thing we did, different kinds of capture. But and we made tools that would actually do this. One was called Voodle, and one was called MacMix, to sort of do different stages of this sourcing project. I'm going to show you one of them, which is, John got a sneak preview of this one.
We present Voodle, vocal doodling for effective robot interaction. When describing something abstract like motion, many people may find themselves at a loss for words, and may opt to use non-word vocalizations to express themselves. Voodle translates the properties of your voice into motion. Voodle detects features like pitch and amplitude and interprets them according to a set of user-definable parameters. With Voodle, users can quickly and naturally sketch effective behaviors in a unique conversational design space.
Let's got best paper at DIS, Designing Interactive Systems, a couple years ago. That was an undergrad who did that project. So we worked with professional, and I should say not just any undergrad, so this is typical in my lab. He was a theater person who happened to have taken a couple of computer science courses, but he's not a computer science person, actually linguistics, I think. He was linguistics and theater, and he knew a bunch of theater people, and to actually work this out, we hired professional sound designers, voice actors, I should say, not sound designers, people who are not shy about using voice. I'll tell you that I've demoed this at a couple of conferences, like myself, not with a student helping me. And I can now separate the world out into two kinds of people. There's the people who will bark at a robot in public and people who will not bark at a robot in public. And think about which one you are, but it's actually kind of fun. So how expressive was Voodle? So here's the three students who worked on this one. And so we have these interesting ways of figuring out when something's working or not. And so what we did was a longitudinal study with our voice actors here. We needed people who were used to using their voices in expressive ways. So here's 3 subjects, P1, P2, P3, three non-normal subjects, people with particular backgrounds. And we took them each through 3 sessions. And in each session, we asked them to play around with it and try and create, using our Voodle tool, trying to create expressive behaviors with a series of different bots. Like we usually had a whole collection of bots that kind of did different things. And then we'd say, how is that working? And they would actually draw on the 2-dimensional scale where they thought they could reach with that robot, what they thought they could achieve with it. And with the robot, the combination of the robot and the tool. And then we'd say, what's wrong with the tool? What do you need? What's wrong with the robot? What do you need? And we'd go and we'd work on the tool. We'd iterate on the tool. We'd iterate on the robots and have them come back and do it again. And by the 3rd time, you could see that they actually felt like they could do a lot more. And I'm sure some of that is they got better at using the tool. But the tool was quite different by the time they'd finished. So it's not just that it's directly translating the audio file into motion. You're actually using different features out of the audio file to do that. So 3 actors using their voices over 3 sessions. So that's a robot display, but I want to talk a little bit about understanding the human affective input, so on the sensing side. So this is also going on. So here's another video I can show you. So who can guess what was going on there? We don't need to listen to that part. Does any ideas of what was going on in that interaction? I mean, how the sensing, from the standpoint of sensing, what was being sensed? Ideas? No DIY wearable people in here. So the trick here is that there's actually, you can see there's a little bit of gleam in the fur. So it's just foul fur, just normal foul fur, but we've seeded it with conductive threads, okay? And when you scrabble those conductive threads together, they touch each other. And we have collectors on the underside, okay? And so the actual resistance, the total, like it's a resistor, and you're changing the resistance in a stochastic way depending on the way you're touching. And it turns out it's very sensitive to the different kinds of touch. You can do machine learning on this, and you can actually tell apart all different kinds of touches. It's actually kind of magical. So the original idea was not ours. This came from Hannah Perner-Wilson, who was at MIT. This is her picture. I keep forgetting to add the attribution there. So this was on a Thingables or something, Thingiverse website. And so these are conductive threads, and she just kind of stuck these different leads and said, hey, when you touch the threads, you can change the resistance between the leads, and you can get different outputs out of it. And that's where she took it. We took this way further and did all these different things of the devil's in the details to make it work really well, and playing around with the different density of the fur and different heights of the threads and all these different things. And finally found you could make just a supremely sensitive instrument out of this and then you add the machine learning to it, and you can detect things that you wouldn't have expected. So we did several studies. The one I'm going to show, we actually added a different kind of sensor underneath, which is measuring pressure. So that one will get kind of different light touches. We were particularly interested in the touch in the air above the surface, the very gentle, soft touches in the fur. But we also wanted to get the deeper touches. And so for that, we're still using this sensor, actually. It's been really, really useful. So electrically striped fabric that you put in layers, and then you kind of get these taxels that are we're using taxels that are maybe, the size of your finger pad, like they're an inch square. And it turns out you don't need spatial resolution. You don't need great spatial resolution. What you need is really good pressure resolution to get social touch. And so we don't need something that's super precise like a trackpad. What we need is something that's kind of crude spatially but very precise in terms of pressure. We need it to be flexible. We need it to be able to sew it to kind of fit whatever shape we want it. We want to be able to put it on squishy surfaces and still work. All of these requirements, and this fabric sensor does that pretty well. It has some drawbacks, but it has worked really well for us. And so we put that underneath and the fur on top. And when you actually do that, so we did a study. So here's the most, remember that touch dictionary? These are the most used, the 9 most used touches. It said, can we tell the gestures apart? This is not the same as sensing emotion, but it's a start. It starts to tell you. If you can tell these apart, you start to be able to do a lot of other stuff too. And so this was Anna Flagg who did this work. And so there's the confusion matrix. It was for 9 gestures. Not too bad. Like it's doing a good job of telling them apart. But this was the really interesting part that was completely, we were hoping for that result on the touch detection. But what we did not hope for was that at the same time we could tell apart the gestures, we could also tell who was touching it. We knew which person was touching it. So this is for different gestures. This is how well you could train it on the person. So you get both gesture and person. Yeah. Yes, this was, I want to just double check. I think it was 16. It was not like hundreds. It was on the order of 16. I should have that written down on the slide. I've rewritten these slides so many times. But so it's not huge, and it's also not a huge number of gestures that we're trying to tell apart. But and I would not say that even on the best ones that 95% is adequate for, say, biometric correction, like you're going to do security on this. But if you have a family device and you're trying to figure out which person has picked it up, it's totally good enough for that. Yes. Yeah, that's a great question. In this case, the robot was not actually moving while we were doing the detection, so we kind of would separate that out. And we later did other studies to say what are all the different factors like curvature, the rigidity of the thing, how much stuff is lying on top of it, and the movement. And it does degrade it, but it doesn't degrade it very much. Like it's surprisingly robust to that. Yeah. Now, again, this is not detecting emotion, and we might have different impact of the movement on emotion because we might be detecting more subtle kinds of features. But this really reinforced to us that we were right, that the pressure is super important, the spatial location not so much. And then we have this whole problem of accessing real emotion. So everything I've showed you up to now is using fake emotion. Simulated emotion is what they call it. This is kind of the state of the art almost in emotion research. It's not just us, but if you're studying emotion in the lab, you typically don't have people who are really feeling the emotion, and you have to ask them to fake it. You can do different things to try and make that a little bit more real, but it's not the same as you're out in the world and you're actually having a moment. And so we've been quite conscious of this and knowing that it was a very big difference, a threat to validity of everything that we're doing. And so the step one is we did a lab study where we were able to just definitely generate real emotions. Like actually it worked so much better than we thought that it terrified us. We realized that we actually needed a therapist on hand because we got people relived emotional experiences. And to our surprise, we found that there were a lot of tears. And we weren't prepared for that. And so I said we kind of generated much stronger emotions in this study than we had been prepared for. So we're writing that one up now, but we also cut that study short. We didn't go to the full amount because we were not sure we had gauged right on an ethical standpoint. And then step two, what we're doing now is longitudinal embedding in real context. This is where we actually go into real places and say, you know, this is going to take a long time, it's going to be hard, but we really need to try and put this in real places and understand how you might actually use these, how you would deploy them in real use cases. So this is, we're calling this haptic robots in care contexts, co-designed with patients and caregivers. I have 2 PhD students who are making this kind of their life work for the next 2 years. Case study relationships. And so this isn't, you just don't drop in and do a study. You become part of the community. You actually have to go and hang out there a lot and listen and work together with the people. So working closely with the caregivers and with the patients in these places, which I'll describe to you. And there needs to be large benefits to the community in our even being there in the first place. This is just a completely kind of research than we had done before. The first place I'd mentioned before, it's Connect Place. And I'll say that just this week we did the first trip in there where we'd have several visits with the current crew. I started talking to them 5 years ago, but we're doing it for real now. And my 2 grad students went in there earlier this week, and they came and debriefed with me afterwards, and they say, you know, we have to rethink how we're doing this because I'm not sure I'm going to be okay. Like this is, I want to do this, but I'm kind of worried about my own emotional well-being on working in this space, and we need to talk about this, which is a first for me, and I have to figure this out. But basically said we went to the debrief, the weekly debrief where all the staff get together. This is actually a physical location, a beautiful mansion in Shaughnessy Heights in Vancouver, where it was a donation, and they have this beautiful home-like place where families can come for respite when they need a break. And the meeting started with lighting the candle for the 3 kids that had died that week, and just kind of went on from there. And it's family-based care, and there's a lot of heavy stuff going on in these places. And if you're actually starting to get close to these kids and their families, it's going to be hard. And so we have to be emotionally prepared for that. So if we wanted to get real, be careful what you're looking for. Another place we're working at is Willow Pavilion Dementia. Willow Pavilion Dementia Center. So this is senior adults who have different kinds of dementia. This is attached to the biggest hospital in Vancouver, in BC, actually in, I think, Western Canada. And this is not just any cases. These are the cases that have not been working out very well, that they need extra diagnosis, extra care. They need to figure out how to deal with particular cases. And again, it's very family-oriented care. They're working not just with the patient, but with the families and caregivers, home caregivers for the patients there. And the people might be there for a couple of weeks. They might be there for 6 months. It's not a long-term care facility. And so again, we're working with the staff, and there's violence there. There's scary situations. There's very sad situations. And we're trying to see if you actually insert the robots into interactions where, for example, an elderly gentleman is violent when he's taking his meds and does not want that, can an object that he's holding and is forming attachment to, can actually you use that to mediate this situation in some way? That just as an example of ideas we're exploring there. And another place, and this is actually a completely different kind of robot, different project that I haven't had a chance to talk about, is at, again, at VGH. We work a lot at VGH. It's actually for premature babies. And so in this case, there's a whole huge project here that is going through commercialization now. So someone who came through the lab and saw an early version of our robot said, I would like to use this with premature babies. This is my colleague Lisa Holste, who's in occupational health and science. And she went to unwrap it and put it on a platform and lay a baby on top of it. And this is a baby who's been born too soon and removed, ejected from the maternal environment and needs that environment back in order to thrive. And so they found that there's kangaroo care is when you put a tiny baby on its mother's chest while they're undergoing a painful procedure. I see some nods. Maybe some people have seen this or been part of this. Usually there's someone in the audience who has. And the baby might have to have a lot of needle sticks and other things that actually cause pain. And we now know that this actually causes developmental damage in the baby to be undergoing these painful procedures. If you can mitigate the pain response, it has a protective effect against these damages. And these are necessary procedures. And so what we have found, and we've just finished the clinical trial on this, is that if you lay the baby on simply a platform that reproduces the mother's breathing, that it mitigates the pain effect. And so you can put this in an incubator, and it helps. Like it's helping the baby recover from this difficult situation. I got involved building the robot, the device, but where I've also gotten involved is there's a very difficult ethical dimension to this particular situation, which is that you can't replace a mom. Like, that's not okay. It's a no-go. It's an absolutely no-go place. You cannot replace the mom. You cannot say, I'm putting a robot in there so mom doesn't need to be there. In fact, the reason we're doing that is because mom can't be there all the time, and we need to provide that protective benefit. But there's a really serious social problem, and it's not just on the surface of it. The moms are, there's a huge potential for depression and feeling unneeded, and it's already very difficult. Nurses would never tolerate it, very protective of the parent, the mother-baby relationship. So we had to design this robot in a way that it didn't do that. And so the trick turns out that if we record the mother's breath motion individually and program that into a device that does not look like a robot, it looks like an appliance, the mother has a very different attitude towards it than if we did not do this. The mother then says, it's an extension of me. And we did a study where we did a qualitative study where we actually looked at this and found that if you can get the mother to identify with the device, with the appliance, rather than she will see of it as an extension of herself rather than as replacing herself. And so this whole idea of kind of understanding how these social robots can actually fit into these very, very tricky situations and be a source of support rather than a source of replacement is also of huge interest and importance. I could talk for quite a bit longer, but I'm going over time, so I'm going to I could wrap up now, or I could talk for a little bit more about a different subject.
I think you could take a few more minutes if you wanted.
I'll take a few more minutes then. Let me see where I can go next. I wanted to talk about design. So I'm going to jump forward to my third challenge. And so this is mobilizing, accelerating haptic design practices. And so what we have here is when we're working in the lab as academics, we have a wonderful freedom. You know, why I love being in academia is that you can really dig deep into a problem. You can spend a lot of time onto it. So some of the things that we do in my lab is we do a lot of prototyping. These are just some snapshots of a ton of different projects we've done. You can see they're low, a lot of them are very low fidelity because we do lots and lots of sketching and quickly trying to figure out how something would go before we really focus on it. And sometimes that goes on to quite heavily engineered, very advanced engineering prototypes. We do a lot of evaluation with all kinds of different weird setups where it's been like years developing an experimental setup so we can actually get at some kind of valid construct and understand what's going on. We would do all kinds of analysis, okay? I've been showing you lots of fluffy stuff that you might think is fluffy. It doesn't look like computer science as you know it, but we do. Like, to have rigor in qualitative methods, which we do quite a lot, is actually, there's a lot of effort that goes into that and trying to understand really what you have and what's going on in the data. So we have all this time to put into this. Sometimes it feels like things take a very long time to do, but it's actually a luxury to be able to dig deep into it. If you're in industry, you do not have this luxury. You need something to go fast. And furthermore, so I've been in the haptics field since the very start. I can say that authoritatively, that the first published haptic device was in 1990. There was others that were before that, and they were built in the lab that I worked in as a master's student at MIT. There's probably others as well. And I started working on haptics in 1990. And so since then, we've gone from the idea of you could build a robot that people could touch, and maybe that's interesting, that you could feel the forces and render forces to people, to having some pretty amazing technology that's out there. But there's this huge gap, which is people don't know how to design content for it, and they don't know how to design it into an application. So there's engineers who can make these amazing machines, and there's human-computer interaction designers who maybe aren't as good at making amazing machines, but have a better idea about how to build stuff. But then you have this design medium that isn't well understood in terms of application design and content development. It's like we know how to do graphic design, we know how to do audio design, we know how to build games and narrative and do things that you can see, but what is the language we use for haptic design, for actually building applications? And so, because we've done so much work on haptic content design, we built all these tools over the years. I've just showed you a few, but we have lots more. How can we actually provide support to this? Because I firmly believe that this is what's stopping the field of haptics from actually having an impact and getting out there, is that no one knows how to design for it. We have technology, but no one knows how to fill it up and use it. And so just define a term, a haptician was a word that one of my grad students developed, just someone who designs haptic devices or experiments, but they have lots of dimensions. So if you're a haptician, you might be coming from many different places in terms of domain. You might be novice or expert. You might be novice in all of those domains. Like maybe you're a student who's just learning engineering and you certainly don't know anything about HCI or psychology. Or you might be an expert psychologist, but you don't know anything about, or very little, about device design or human-computer interaction development. A very important group of people is what we call enthusiasts, people who maybe don't know much, but they're really excited about it, and they're willing to learn, and they're trying to explore, and they're trying to figure out how to access this fascinating field. And then what are you actually trying to do with it? Are you trying to build a device? That's what the engineers are doing. So I'm coming from the engineering community, and I spend a lot of time talking to people. This is what they're doing. They're trying to make a device that can solve a technical problem. Haptic content, are you actually trying to build experiences? Or the entire end user experience. For haptic content, maybe you're just trying to build like a set of haptic icons or a particular effects to use for a game. Okay, and then who is it for? Like the experience you're trying to build, is it like everyone? Like you're making better buzzes on your cell phone? You're like, so a signaling system that a broad category of people would use? Or is it going to be something like a surgical simulator that is really intended for medical students? Or is it for yourself? You're customizing something that you're going to use yourself. So that all makes a difference. And what design stage are you at? Is it early concept where you're trying to sketch and figure out a broad range? Is it you're trying to improve and refine it and add detail and invest in it? Are you doing field testing? What stage are you at? What tools you need are going to be very different for all of these things. And so we've been doing some development in these. The shaded things are places where my lab has done something. You can see there's a lot of gaps. And if there's a shaded thing, it doesn't mean we've mastered it. It just means we've poked at it. There's a very big space to do. So if I want to go very quickly over kind of the whole idea of process, we start by actually saying, let's bring the idea of process to haptic experience design, because that's something that's quite well understood in other domains of experience design. The HCI community has quite accepted ways of teaching this, for example. But people designing haptic experiences, because they often come from the engineering community, don't have any of that ethic. They're very good engineering designers, and they have an idea of process from that standpoint. That's different than user-centered interaction design. So the different things that we do at different stages of design, and so this is not our list, but so for primary activities, and you could probably come up with more, but we found when we actually both combined literature on interaction design, but also designing with different kinds of media, not haptic media. And then we also studied professional haptic designers to see what they do. And we can pretty much categorize almost everything they do into these groups. So you want to browse, you want to look for examples, you want to see what else have been done, you want to search for content. Like you're making a new website, you look at other websites, you look at the HTML behind them and figure out how they built them. You're making an image, or you're looking for different kinds of photo effects. Maybe you go and look at image galleries. So the first thing you do is you go out and search, right? Okay, what can we do to browse haptic stuff? It's like, good luck with that. It's very difficult. Doing that initial sketching part, I've talked a little bit about those problems. Editing, you have an initial idea, now I want to make it better. Are there tools that actually help you refine it? I want to share what I've done, but not everyone has the display that I can feel. Like all of these things, we do them with other kinds of design, but there's huge obstacles to doing them with haptics. And so using this framework, we've looked at, we can sort our own tools into these different groups, and then we want to go and say, where are the gaps? What needs to be done? One of the reasons that makes it so hard is that the haptic hardware is very, very diverse. There's so many ways that you can actually create a haptic sensation. One of the projects that I don't have time to show you, we call it Haptipedia. You could look it up, haptipedia.org. It's a collection of all the force feedback devices that we can find that have ever been invented. and there's all this information about them and all these ways of browsing them. And it was there because I got tired of people asking me, one of the old people in the field, who's ever invented this kind of mechanism? Because I want to see all the prior art on that. And it's like, I can't remember. My memory is not so good. We need to find these in a place because otherwise people are just reinventing the wheel and they don't know what to build on. So if we're browsing, I'll just say a brief idea of the browsing problem. So you're trying to make haptic icons for vibrotactile signaling, which is something that everyone can probably relate to. We don't have a design language. We don't have words for these things. Instead, if you're an engineer trying to make these, we say the discourse is grounded in machine parameters. So if you have the designer, he's thinking things like frequency, duration, amplitude, waveform, all these technical terms which relate to the signal that I'm sending out and how I can control it, okay? You guys are all computer science, you get this. All right, but here's the user, and he's thinking in a very different language. And there's no connection between those two. Like, what should urgent be in terms of frequency, duration, amplitude, waveform, rhythm? We don't know. But that's what if Todd was going to design these, he wants to make it more urgent, more musical, more like a motorcycle. Okay, that's what he wants to design in, and the designer needs to be doing that too. So that disconnect is something that one of my students, Hasti Saifi, dug very far into. She's now a postdoc at Max Planck in Germany. So look at the cognitive frameworks that people use when they're trying to understand things. And so these are some cognitive frameworks that she came up with for this particular space. There's physical structure, sensory attributes, emotional connotations. See, emotion, if you look at the words people use to describe haptic sensations, emotion's very, very prominent in them. We keep coming back to this emotion thing. And so then she made a huge library of tactile sensations. Some of them we made, some of them she collected, other people's libraries, everything she could find and threw it in there. And actually used visualization, a browser, so that you could actually you do faceted browsing to look at these things from different ways, from different cognitive frameworks. So you have the same library, okay? And then you can just, you can browse this library from all these different perspectives. All right, so that you can look at the set from the physical view. So every dot is a tactile sensation, and you're looking at them organized according to different, the different panes are the different frameworks. So that if I pick one, I can see where it shows up in the other way. So this is called faceted browsing. It's a visualization thing. This is one of this idea of where I have a colleague who's an expert in visualization, and she taught us how to do this, and we said, wow, this would be really. It's not that you're using visualization in the haptic interface, you're using visualization to help you as a design tool. And so we call this VibeViz. It's available online. You can play with them. You can see what the signals actually look at. You can download them. You can use them. But all you can do is browse. You can't do anything else. And so if you want to actually construct a new device, that's a whole different problem. There's creating. It's not, and I would say that something here, and Sean and I were bemoaning this again, a lot of my colleagues in engineering, they'll say, we're doing application design. We are saying that this new wearable haptic device will be good for people with a particular kind of physical impairment, okay? And we'll design this device. Have they ever talked to a person with that physical impairment? No. Do they actually know what problems that person with physical impairment has and what needs they have and why they will never, until hell freezes over, ever wear this thing, okay? Because even if it worked for them, no, they're not doing that. They're just saying, theoretically, we think it could be used for that device. It's a very common approach that engineers take to designing technology that they intend for human to use. And so what we're trying to do is get past that and actually go into this. So into content design in a more careful way. Most haptic applications are multimodal. They're going to be using different senses together. You don't usually just feel it. You also see it, you hear it, and trying to come up with that whole experience. And so, and this would be a longer talk, haptics can take many roles in an interaction. We've gone into this and studied it and tried to, again, make frameworks. Is it a primary stimulus? Is it reinforcing? Is it the first thing you do? Or is it something like maybe I get an alert and then I go to a visual medium to follow up on what that alert was? Because haptics might be good for unintrusive notification, but it might not be so good for giving you detailed follow-up information. I'm trying to say, what is haptics good for? How can it play? Like, think if you're doing a theater design and you have different actors in a stage play, and how are you going to kind of have the different roles and make them work out? And so we have all these scenarios we've developed about the different roles this can take and try and start to lead people through this problem of haptic content design. But then you need authoring tools, and so we've been developing the authoring tools. There's a couple of examples that I showed you, the Voodle and the Cuttlebit design systems. That would be an example of what I mean by authoring tools, where they are quick, easy sketching. They might not be the final thing, but they let you explore a design space very quickly. But those were intended for a particular purpose. They were for trying to create expressive robot motion. You might adapt them for other purposes, but there's some things that they won't adapt to, and you have to do something else. Okay, and then I am going to wrap up now. There's the slides on editing and sharing, and we have tools for that. And so I can just kind of show you our whole design space here. These are some tools that we've built under these different categories, but you can see how a framework might emerge. And so what we're actually trying to do is think about the design funnel. So this is a classic Bill Buxton inspired figure where it's not invented by Bill Buxton, but this whole idea of you start very broad and then you narrow down and refine to, as you reduce risk, you're also increasing investment. And so that's what the funnel means, is that you have lots of ideas that are very cheap, and then you have a final prototype that's very expensive, but you're more confident because you've done a lot of exploration. And so where these different tools that we're talking about might work out. So you're sketching early in the design process, you're refining at the end, or kind of all throughout here. It's a kind of a spectrum. And then sharing and browsing. You can only browse what has already been shared. And so trying to create this virtuous cycle where people are sharing their designs so that we can browse them and making tools that allow you to browse them. And then you can kind of feed that all in there. And so we're trying to support this kind of design ecosystem. And so it's not enough to have tools that work in isolation. I've shown you a few tools. They work in isolation. But if you want to say, I'm starting with a sketch and now I want to move it in, think about Adobe tools, that you can kind of move for a graphical design all the way from an initial sketch and kind of carry that same format all the way through. Can we ever do that for haptic design? And so we are working on trying to develop that kind of a thinking, and that's sort of our big push right now, is this open haptic repository. I'm going to, because I know there's lots of students in the room, I'm going to close with one particular thought that I want to leave you with. It's been very forefront in my mind over the last few years, especially with this huge emergence of AI being so important and all these huge ethical issues that are showing up that you read about all the time, and you're a computer scientist, and you're thinking about, what are my responsibilities here, and how can I make the world a better place? And so we have incredible power, and computer science is very, very central in where technology is going these days, and you guys are going to be leading the curve. There's a responsibility as technologists that we cannot turn our backs on. And so I showed you a simple idea about a little robot. It's very simple, actually, although it might have a lot of computer science inside it with the sensing and the smarts it can do. So let's say my vision comes true and I can send these little bots home, and a therapist can use it as an adjunct to help a kid who's really struggling with something. And the child becomes attached to this precious object and takes it everywhere with them and talks to it and cries with it. And this little object is with them, and through all the emotional turmoil that's going on in their house, it knows her, it knows its family. And so this is a very intensive private data generator. It could be very misused. Okay, so what can I do about that? I don't know, but something needs to be done. I need to think about that. So I'm trying very hard to create this little thing, but it could be misused. So this is something that I have to be thinking about in parallel. And whatever you're doing, it's probably the same thing. I know John works on vision research. I think everything I'm saying you could say all the more for vision research. It's a huge problematic issue in terms of privacy, and privacy, of course, is just one thing that we worry about here. So as computer science becomes more high profile and more important, I think how it works in society and what our ethical applications there grow along with it. And so think about that. I also wanted to say I'm running a research cluster at UBC called Designing for People that I'm very excited about. We're about 3 or 4 years in now, so not as long as the cluster that John's running here. I just want to do a little plug for it. We're growing all the time. I think we're at 24 core faculty right now and 11 departments, so it's very, very cross-disciplinary. And we support collaborative research, building clusters. We have a grad training program, a big seminar series that 80 or 100 people come to every 2 weeks, and a lot of support for people getting their ideas out into the world, which has often been very hard in the computer-human interaction area because you spend all this time trying to design things that will help people, and then maybe they're not going to be a big commercial win, so it's hard to use the traditional licensing and patenting in startups. Or maybe there's no company that wants to buy the technology. And so how do you actually get into the hands of people it was intended to help? So we're trying to figure out pathways to do that. And for students, at least the master's students in the room, or undergrads, we do have this grad training program that's again, very interdisciplinary. We have participating, these are most of the departments, several engineering departments, computer science, information school, architecture, nursing, psychology. You can see there's a very diverse mix of students are coming together, and faculty, supervisors, so that these students can learn how to work in teams and solve the harder problems that need those different perspectives. And I will tell you, it is not always easy. You have a lot of different languages to learn. Just even my CS students working with their psychology collaborators, some of the most amazing misunderstandings that come up. It's pretty hilarious, but I think we're all learning from it. So if you are thinking of a PhD, please do consider us. I think it's a really exciting program, and it's in British Columbia. So anyway, some of the students who have been working on this research that I've talked about today. There, wow, I took quite a while, and my voice is still working.